So welcome to our third video on section 2.1, and we're going to begin with the idea of what is a cardinal number. And so your goal is going to be, you should be able to say, I can find the cardinal number of a set. So before we can say that we can do that, we have to ask ourselves, what is a cardinal number? Well, all a cardinal number is how many elements are in the set. So all we have to do is figure out how many elements are in the set. And the way we illustrate that, if we have set A, then we write this notation, the number of elements in set A. And this notation is the cardinal number. So it's either the number of elements in the set, or you can call it the cardinal number. Either one of those is correct. So let's do a couple of examples. So you might want to take a moment to write these three examples down and then try and solve each one of them. In each case, you want to find the cardinal number. So as I look at number 1, I want to find the number of elements in set A, or the cardinal number. Well, this one's easy. All of these are listed by the roster method, and I can see there are 1, 2, 3, 4, 5. So there are 5 elements, and so in this case, the number of elements in set A is 5. Now when you do your homework, this would be considered a complete problem. Write down the set you're talking about, and then find the number of elements in the set. So let's look at the next one. Go ahead and try that. Pause the video, and then come back. Okay, now this one's a little more challenging because it's in set builder notation. What that means is we might want to make a roster of which elements satisfy that. So the set of all x, so I'm going to get my roster ready. Set of all x such that x is a day of the week which begins with an A. So let me think. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Well, none of those begin with an A. So this is the correct roster. So the number of elements in set C is 0, which are the number of elements in the empty set. In this case, this was the empty set. C was equal to the empty set. We're going to talk about equality of sets in a moment. So that takes us to B. And B says, the set of all x such that x is a natural number and 2 is less than or equal to x is less than 7. So what do you think the solution is? Well, the easiest way to do it is to just do the roster. Well, that's 2, 3, 4, 5, and 6. It doesn't include 7 because it's strictly less than. And so, as you can see there, and so once again there are 5 elements, so the cardinal number of set B is 5. Now these are the kinds of things you can do to actually show work. You write the problem, then you answer the question. So make sure you start using correct notation as is used here in each of these cases. Okay, let's go on to the next topic. So the next topic is equivalent sets or equal sets. And what's the difference? Well, equivalent sets are basically the same size. In other words, they have the same cardinal number. Okay? Equal sets, not only do they have the same cardinal number, they're the same size, but they have the exact same elements. Okay? Every element in one set is an element in the other. And so that means that they're exactly the same set. So that's a big deal, and you want to keep that in mind. So here's a couple of examples, and I'll write them down just a sec. So here we are with two examples. You might want to take some time, write both down, and then take a look at them. And so we're going to decide if they are equal or equivalent sets. So let's look at number 1 in the blue first of all. So number 1 has the set with 1, 1, 1, 2, 2, 3, 4. Well, one thing we know about sets is we don't have to list the same element twice. So this set is actually the set containing 1, 2, 3, 4. And therefore, what I can see, if I look at this closely, they both have a 1, they both have a 2, they both have a 3, and they both have a 4. So that means that these sets are equal. So I can say A equals B, and A is equivalent to B. Saying it's equal is also saying it's equivalent, but it's okay to say both like this in this case. So let's look at number 2. So number 2 is a little different. We're given set builder notation. So what I would like to do is write the rosters. So natural numbers that are between 12 and up to and including 17. So this is 13, 14, up to 17. The cardinal number of that is 5. Okay, the number in set A is 5. And this set is 20, 21, 22, 23, 24. It also has a cardinal number in set B is equal to 5. So right away I can see that set A is not equal to set B in this case, but A is equivalent to B. In other words, they have the same number, the same cardinal number. Okay? Now you can have situations where the sets are not equal and not equivalent, and basically one set has to have at least one more element than the other. So the last idea is the idea of finite and infinite. So a finite set is a set whose cardinal number is a finite number. So for instance, if I had a set A equal to 1, 2, 3, then the cardinal number, the number of elements in set A is 3. 3 is a finite number. It's a number that you can actually count to. Therefore, this is a finite set. However, if I said set B was equal to the set of all x, such that x was a natural number, and x was greater than or equal to 10, well then if I start to list that roster, that would start at 10, 11, 12, and then it'd be an ellipsis going on and on forever like that. So in this case, the cardinal number here is not a finite natural number, so therefore this set would be infinite. And so they try and play that game with you. A little trick they might do is they'll give you a set C, and they'll say like the set of all x such that x is a natural number and x is less than or equal to 2 million. Oh, let's just go crazy. Let's go to 2 billion. Alright? Well, if that's the case, even if I start listing the roster method, 1, 2, 3, dot, 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 then I go 1,999,999,999, and then the next number is 2 billion. You can see that this is still a finite set. The cardinal number, the number of elements in set C, is 2 billion. Alright, which is a finite natural number. So it doesn't matter how big this number is. If it's an actual number you could count to, given enough time, then that means it's a finite set. Okay? We're going to come back. That's the end of these videos. We're going to come back, and in class you are going to focus on problems from 67 all the way to the end of the section. So I'm going to give you some problems that are a little bit more challenging. 126. Now I won't give you a bunch of those, but up to 96 I'll probably do something like multiples of 3 or 4 or something like that. And then once we get past 96 I'll pick a couple, just so you know. And that's what you'll be working on in class. So if you want to look over those problems and just get a feeling for what you're going to be doing, then just let me know. Okay? If you have any questions, make sure you bring them to class. Okay? Bye.